Okay, so now let us look at some of the problems here. So first, we computed the determinants by the cofactor method and for the following matrix. So for the first one, we can use the very standard method to figure it out. That is, we can go through either through the first row or the third column, right? Why? Because it gets involved with a zero for one of the entries. So if we go through the first row, so it's going to be 4, right, to the power of negative 4 times negative 1 to the power 1 plus 1 times the determinant of a 5, 2, 7, 3, right? Plus 3 times negative 1 to the power of 1 plus 2 times the determinant of 6, 9, 2, 3, right? And then plus 0, blah, 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 right? Then this part is 1, this is negative 1. So the determinant of this is so 4 times 5 times 3 minus 2 times 7, right? This is minus, so it's minus 3 times, well, it's 6 times 3 minus 2 times 9. So it gives us this 15 minus 14 is 1, so it's 4 minus 3 times it's 18 minus 18 also is 0, right? And then it gives us this is times 0, so this gives us is 4. Okay, that's the first one. The second one, take a look. This is a 5 by 5, and for a problem like this, especially the size is large. Typically, we will go through either the row or the column which has the most zeros, okay, which has the most zeros. So as you can see that we can go through with the second column, right? So you will see it's going to be 3. So since this is the third row, second column, times negative 1 to the power of 3 plus 2, right? And then times the determinant of this, right? So it's 4, negative 7, 3, 5, 0, 2, 1, 0, 5, 5, 1, negative 6, 0, 3, 2, 1, right? Okay, so that's something what we need to do. And now, so this is negative 3, right? So if we look at here, realizing that for this submatrix, we can either go to the second row because it has 2 zeros, or we can go through with the first column, right? So it's going to be negative 3 times, let's see, 4, right, times the determinant times the determinant of This is 2, 1, 0, 5, 1, negative 6, 3, 2, 1, right? And then plus 5 times negative 1 to the power of 3 plus 1 times the determinant. So it's a 4, 0, right? Oh, excuse me. So I think I made a mistake. Yes, that's going to be negative 7, 2, 3, 3, 1, 2, 5, 0, 1, right? That's something what we can get. So it turns out, you see, this part is also positive. This part is also positive. So what we can do, we just need to go over with those two. So it's a negative 3 times 4 times, this is going to be 2, right, times the determinant of 1, negative 6, 2, 1, right, minus 1 times, I just ignore the determinant, okay. So it's 5, 3, negative 6, right. And then plus 5 times, we can go through, you know, with any of them, but maybe we can go through with the second row. So it's times 2, right, to the power of negative 1 to the power of 2 plus 1 times the determinant of, so it's a 3, 5, 2, 1, right, and then plus 1 to the times negative 1 to the power of 2 plus 2, so it's times the determinant of negative 7, 3, 5, 1, okay, yeah, and then close this big parenthesis. I think we need more paper to continue this. Let's write it down here. So for this pieces, you see, so this is one parenthesis, this is not a parenthesis, there's a big one. So it's negative 3, 4 times, right, 2, the determinant of this pieces, right. So it's 1 times 1 is 1, minus 12, so it's going to become plus 12, so it's 2 times 13, okay. And then minus, this is 1, okay. So it's a 5 minus negative 18, so it becomes into plus 18. So it's a 5 plus 18 is 23, so minus 23. Okay, so then plus, okay. So we have 2, so this part is going to be negative 2 times 3 minus 10, so it's negative 7, right? And then so this is negative 1 to the power 4 is positive, so it's plus 1 times this, so negative 7 minus 15, right? Okay, yeah, so that's it. And then we can do, so this is 4, so it's 26 minus 23, okay, plus 5. So for this part, I have 14, right? I have minus 22, okay. And then let's see, so it's negative 3. So this part is a 4 times 3, right? plus 5 times, this is negative 8, right? So you have negative 3, this is 12, minus 40, right? So it's negative 3 times negative 28, and then the answer is going to be 84. Okay, 84. So that's how to handle this one. Okay. Now problem 2 is said that what is 5a? A is given, so 5a, which is 15, right? 5, 20, and 10, right? So the determinant of this 5a matrix is going to be 150 minus 20 times 5 is 100, right? Just 50. While the determinant of A is 3 times 2 minus 1 times 4, which is 6 minus 4 is 2, right? So determinant of 5a, do you see equals 50? The 5 times determinant of A, 5 times determinant of A equals 10. So hence those two are the same. Okay. Part B, find the determinant by the row reduction to this echelon form. Keep in mind that is when you multiply one row and add it to the other one, and then the determinant is going to be equivalent. And then if you do the swap, and then the determinant is going to be the negation. But if you do the scalar to any of the row, it's going to be the scalar multiple of the determinant of the new matrices. Okay, so from here we can see if we use the row 2 plus row 1 give us a new row 2, you see the matrix is going to be 0, right? 1, and we have 1 here. And then if we use row 3 plus 2 times row 1, that would be to the new row 3. It's going to be 0. This part is going to become into 2. This part is going to become into negative 1, right? So that's something we get. Okay, we get. And then we can continue to do that, you know, because right now the determinant of this guy and this guy is going to be the same. Now we can continue to let row 3 to minus 2 times row 1, right? And then let it become the row 3. So you see we're going to have it 1, 5, negative 4. We're going to have 0, 1, 1. And then we're going to have 0, 0. So negative 1 minus 2 give us is negative 3, right? So right now we should be good, because right now this is the upper triangular form. So the determinant of this, suppose this is matrix A, determinant of this matrix is going to be the multiple of the main diagonal entries. So it's 1 times 1 times negative 3, which give us is negative 3. Okay, so that's a problem here. Moving on, to use a determinant to decide if the set of vectors is linearly independent. You know, this is fairly simple. You know, so you have 4, 6, 2, negative 6, 0, 6, negative 3, negative 5, negative 2 here. So if you list them in terms of matrix, if the determinant is not 0, and then it's linearly independent. Otherwise, it's going to be linearly dependent. Okay, so basically, all you need to do is just figure out the determinant, and you can do a couple of ways. We can follow from the second column, okay, to handle that. So it's a negative 6 1 plus 2 times the determinant of 6 to negative 5, negative 2 plus 0, and then plus 6 times negative 1 to the power of. This is the third row, second column, right? Times the determinant for 6, negative 3, negative 5. So this is going to be positive 6 times negative 12 minus 10, so it becomes plus 10. This is minus 6 times negative 20 minus 18, so it becomes plus 18. So this is 6 times negative 2 minus 6 times negative 2, right? So this is going to become into I think this, hold on, that means I think this is going to become into a 0, right? So if this is 0, then do you see it's going to be not independent, right? Not independent. So that's very good to see. Okay, cool. Now next one, problem 3. A is here, B is given. They ask us to show that if the determinant of A plus B equals determinant of A plus determinant of B, if and only if. So basically A plus B is going to be 1 plus A B, right? C 1 plus D, right? So the determinant of A plus B, which is 1 plus A times 1 plus D minus BC, right? Well, determinant of A equals 1. Determinant of B equals AD minus BC, right? So as you can see, if you expand this part, this equals 1 plus A plus D plus AD minus BC, right? So you can see if you want to let the determinant of AB equals determinant of A plus determinant of B, you realize that you need to make sure 1 plus A plus D plus AD minus BC equals 1 plus AD minus BC, meaning A plus D can be 0. Okay, so yes, it's easy to handle. Okay, so I'll stop here and then I'll be back.